A complex polynomial, say p of z, is an expression of the form an set to the n plus an minus 1 set to the n minus 1 plus all the way to a1z plus a0, where ai are complex numbers and z is also a complex number. N is called the degree of p of z, denoted by deg bracket p of z. ai is the coefficient of zi. An, which is the coefficient of Zn, is called the leading coefficient of p of z. Also, for lambda, a complex number, we say that lambda is a root of p of z if p of lambda equals 0. An elementary but important result for polynomials is the factor theorem, which states that lambda is a root of p of z if and only if z minus lambda is a factor of p of z. To prove this, suppose that z minus lambda is a factor of p of z. Then we can write p of z equals z minus lambda times q of z for some polynomial q of z. So p of lambda equals lambda minus lambda times q of lambda, which equals 0. That is, lambda is a root of p of z. Conversely, suppose that lambda is a root of p of z. We write p of z equals an set to the n plus an minus 1 set to the n minus 1 plus all the way to a1z plus a0. By substituting z equals lambda, we have p of lambda equals an lambda to the n plus an minus 1 lambda to the n minus 1 plus all the way to a1 lambda plus a0. So p of z minus p of lambda equals an times z to the n minus lambda to the n plus an minus 1 times z to the n minus 1 minus lambda to the n minus 1 plus all the way to a1 times z minus lambda. Label this as star. Now, we note that z to the k minus lambda to the k equals z minus lambda times z to the k minus 1 plus z to the k minus 2 times lambda plus all the way to z times lambda to the k minus 2 plus lambda to the k minus 1. This is true for all positive integers k. So, z minus lambda is a factor of z to the k minus lambda to the k for all positive integers k. From star, we know that z minus lambda is a factor of p of z minus p of lambda. Since p of lambda equals 0 by assumption, z minus lambda is a factor of p of z, hence completing the proof. Let's look at an example. We want to factorize the polynomial p of z equals z to the 7 minus z to the 6 minus 2 times z to the 4 plus 2 times z cubed plus z minus 1 completely. First, we have p of 1 equals 0, so z minus 1 is a factor of p of z by the factor theorem. By inspection, we can take out the common factor z minus 1 by grouping the terms of p of z as z to the 6 times z minus 1 minus 2 times z cubed times z minus 1 plus z minus 1, which equals z minus 1 times z to the 6 minus 2z cubed plus 1, which equals z minus 1 times z cubed minus 1 squared. To split z cubed minus 1, we need to solve z cubed equals 1. The solutions are 1 e to the 2 pi I over 3 and e to the 4 pi I over 3. So p of z equals z minus 1 times bracket z minus 1 times z minus e to the 2 pi I over 3 times z minus e to the 4 pi I over 3 whole squared, which equals z minus 1 cubed times z minus e to the 2 pi I over 3 squared times z minus e to the 4 pi I over 3 squared. Now, we introduce the Fundamental Theorem of Algebra, or FTA for short, which states that every polynomial of degree at least 1 with complex coefficients has a complex root. That is, if p of z equals an set to the n plus an minus 1 set to the n minus 1 plus all the way to a1z plus a0, where ai are complex numbers, n is at least 1, and an is non-zero, then there exists a complex number lambda such that p of lambda equals 0. The proof of this result requires knowledge in complex analysis, so we will skip the proof here. The FTA has several important corollaries, and we shall discuss only a couple of them here. Let p of z be a complex polynomial of degree at least 1. Then p has exactly n roots, counting the repeats. That is, there exist complex numbers lambda 1 up to lambda n such that p of z equals an times z minus lambda 1 times z minus lambda 2 all the way to z minus lambda n, where an is the leading coefficient of p of z. We will prove this result by strong induction. The base case is n equals 1, in which case p of z equals a1z plus a0, which equals a1 times z plus a0 over a1. Since a1 is non-zero, p of z has exactly one root, namely negative a0 over a1. So the base case is true. Assume inductively that the corollary is true for all degrees of p of z being less than m. Now suppose that the degree of p of z equals m. By the Fundamental Theorem of Algebra, p of z has a root lambda 1. By Factor Theorem, p of z equals am times z minus lambda 1 times q of z for some polynomial q of z. Since the degree of q of z equals m minus 1, which is less than m, we can apply the inductive hypothesis to q of z to deduce that there exists lambda 2, lambda 3, up to lambda m, such that q of z equals z minus lambda 2 times z minus lambda 3 all the way to z minus lambda m. Hence, p of z equals an times z minus lambda 1 times z minus lambda 2 all the way to z minus lambda m, which completes the proof. Now, let's look at the second corollary. Let p of z be a real polynomial of degree n at least 1. Then, p of z can be written as a product of linear and quadratic polynomials with real coefficients. To prove this, we first make use of the first corollary to write p of z equals an times z minus lambda 1 times z minus lambda 2 all the way to z minus lambda n for complex numbers lambda I. If all of the lambda i's are real, then we are done. Otherwise, there exists a lambda, which is lambda I for some I, which is not real. Then we have an lambda to the n plus an minus 1 lambda to the n minus 1 plus all the way to a1 lambda plus a0, which equals 0. Taking complex conjugates, we have that 0 equals the complex conjugate of an lambda to the n plus an minus 1 lambda to the n minus 1 plus all the way to a1z plus a0. Using the properties of the complex conjugate, we can write this as the complex conjugate of an lambda to the n plus the complex conjugate of an minus 1 lambda to the n minus 1 plus all the way to the complex conjugate of a1 lambda plus the complex conjugate of a0. Since the ai's are real by assumption, their complex conjugates are just themselves. So we can further simplify the expression to an lambda bar to the n plus an minus 1 lambda bar to the n minus 1 plus all the way to a1 lambda bar plus a0. This is just p of lambda bar. This implies that lambda bar is also a root of p of z. Since the complex roots of p occur in pairs, it remains to show that z minus lambda times z minus lambda bar has real coefficients. Now, z minus lambda times z minus lambda bar equals z squared minus bracket lambda plus lambda bar times z plus lambda times lambda bar, which equals z squared minus 2 times the real part of lambda times z plus the absolute value of lambda squared. Since -2 times the real part of z is a real number, and the absolute value of lambda squared is a real number, we are done. Now, consider the polynomial p of z of the form z minus lambda 1 times z minus lambda 2 all the way to z minus lambda n. If we expand the brackets, we have p of z equals z to the n plus an minus 1 z to the n minus 1 plus all the way to a1z plus a0, where an minus 1 equals negative the sum of lambda I from I equals 1 to n, which equals the negative of lambda 1 plus lambda 2 plus all the way to lambda n. An minus 2 equals the sum of lambda I times lambda j, where I is less than j. An minus 3 equals negative the sum of lambda I times lambda j times lambda k, where I is less than j and j is less than k, and so on, until a0, which equals -1 to the n times lambda 1, lambda 2, all the way to lambda n. As an example, let's try to find a cubic polynomial with roots lambda 1 equals 1, lambda 2 equals 1 plus I, and lambda 3 equals 1 minus I. We let the polynomial be p of z equals z cubed plus a2z squared plus a1z plus a0. Then a2 equals the negative of lambda 1 plus lambda 2 plus lambda 3, which equals the negative of 1 plus 1 plus I plus 1 minus I, which equals -3. a1 equals lambda 1 times lambda 2 plus lambda 1 times lambda 3 plus lambda 2 times lambda 3, which equals 1 times 1 plus I plus 1 times 1 minus I plus 1 plus I times 1 minus I, which equals 4. a0 equals negative lambda 1 times lambda 2 times lambda 3, which equals negative 1 times 1 plus I times 1 minus I, which equals -2. So p of z equals z cubed minus 3 times z squared plus 4 times z minus 2.